Have you ever wondered how self-driving cars or robots can safely navigate the real world? It's not just about smart algorithms, it's about safety. But here's the catch. When AI systems interact with complex, unpredictable environments, ensuring they're always safe is like trying to predict every possible way a storm could hit. It's practically impossible. Today, we're diving into a groundbreaking approach called provable probabilistic safety, a smarter way to make sure AI systems, like autonomous vehicles or medical robots, are safe enough for real-world use. Let's break it down. First, let's talk about the problem. Embodied AI systems, think robots, drones, or self-driving cars, have to deal with two huge challenges. The first is the curse of dimensionality. Imagine trying to map every possible scenario a self-driving car might face: different weather, road conditions, pedestrians, and more. The number of possibilities is astronomical. Checking every single one for safety is like trying to count every grain of sand on a beach. Impossible. Then there's the curse of rarity. Safety-critical events like a car crash or a robot malfunction are super rare. But that's a problem. If you can't test for these rare cases, how do you know the system is safe? It's like trying to design a parachute without ever testing it in a real fall. So how do we solve this? Enter provable probabilistic safety. Instead of trying to prove safety for every possible scenario, which is unrealistic, this approach sets a risk threshold. Think of it like a safety net. As long as the system's risk stays below a certain level, it's considered safe. For example, a self-driving car might need to have a crash rate of less than 5 in 10 million miles. Super low, but achievable. Here's the magic. Instead of exhaustive testing, researchers use statistical methods to estimate and reduce risk. It's like using weather forecasts to prepare for storms, rather than predicting every single raindrop. This makes safety verification feasible for complex systems. And the best part? The safety guarantees can keep improving over time, as more data is collected. But how does this work in practice? The paper outlines 3 key questions. 1. What is provable probabilistic safety? It's a framework that balances rigor and practicality, focusing on measurable risk rather than impossible perfection. 2. How do we prove it? By combining mathematical models with statistical analysis, researchers can show that risk stays within bounds. 3. How do we achieve it? Through techniques like intermediate models, simplified simulations, and direct statistical testing, ensuring systems are safe enough for real-world use. This isn't just theory, it's a game changer. Imagine a future where AI systems in healthcare, transportation, and beyond are both powerful and safe. By embracing probabilistic safety, we're paving the way for AI to scale responsibly, without compromising on reliability. But safety isn't just about avoiding disasters. Take control barrier functions, CBFs, for example, mathematical tools that act like invisible walls to prevent AI from making dangerous decisions. If a self-driving car is about to swerve into a pedestrian, a CBF forces the system to choose a safer path. It's not about perfect prediction, it's about bounding risk, ensuring the AI never strays into catastrophe. Then there's the challenge of truth. Large language models like those powering chatbots can hallucinate, spout facts that sound real but are completely made up. Researchers are tackling this with semantic entropy, a metric that measures how uncertain an AI's output is. If the entropy spikes, it's a red flag. The AI might be fabricating information. And let's not forget the real-world test. AI doesn't live in a lab. It's out there in traffic, in hospitals, in our homes. To prepare for that, scientists are building simulated environments that push AI to its limits. Imagine a virtual city where AI must handle everything from sudden rainstorms to pedestrians darting across the street. These tests aren't just about speed or accuracy, they're about resilience. The takeaway: AI safety isn't a single fix. It's a mosaic of techniques, math-based proofs, real-world simulations, and clever checks for truth. Researchers are working tirelessly to ensure AI isn't just powerful, but trustworthy. So the next time you interact with an AI, whether it's a voice assistant, a recommendation algorithm, or a self-driving car, remember, behind the scenes, scientists are building layers of protection. Because the future of AI isn't just about what it can do, it's about how safely it does it. What do you think is the biggest hurdle in making AI safe? Drop your thoughts in the comments, because the future of this technology depends on all of us asking the right questions.